continue looking at polynomial graphs and talk about how to graph polynomials without a calculator. So the first thing you want to do is look at the polynomial and think about what we learned yesterday. Its general important features. So here my degree is 3, so it's a cubic function, and the leading coefficient is positive. So when I have a positive leading coefficient on a degree 3 cubic function, that function is going to be a down-up. So it's going to start down and end up, very much like our parent x cubed. What we need to decide is what it looks like in between. Well, the other thing we learned yesterday is that math is consistent and we can find the y-intercept. Here there is no constant term, so our y-intercept must be 0. And something that we've been doing for years now is factoring polynomials. And so what we'll do to find the other x-intercepts or zeros or roots or solutions is factor this polynomial. So we're going to take our x cubed minus x squared minus 12x and set it equal to 0 in order to find those factors or zeros on my graph. This function has a common x as a factor, so I'll take that out and I'm left with x squared minus x minus 12. This is a trinomial. I can factor it using product sum. I need two numbers that multiply to negative 12 and add up to negative 1. Because the leading coefficient now is a 1, I can do a quick factor, and my factors are x minus 4 and x plus 3. Make sure you always multiply that back out quickly in your head to make sure you've factored right. As always, when solving by factoring, we set all of our factors equal to 0. So here, x equals 0. X minus 4 equals 0, so x must be 4, and x plus 3 equals 0, so x is negative 3. Well, now I have 3 x-intercepts, so I can start sketching this graph based on everything I know. So I have a y-intercept of 0, which is also one of my x-intercepts. X equals 4 is another x-intercept, and x equals negative 3 is my third x-intercept. I know that it starts down, so it's going to do something like this, and it ends going up, so it's going to do something like this. We're curious about what's happening in between the zeros, and it's not super important that you have an exact graph at this point, but what we'll want to do is take one of these numbers in between and find its value, and then turn around that point and finish drawing a nice general sketch. So for this one, I might look at x equals negative 1, and maybe x equals negative 2. And we'll plug it into our function x cubed minus x squared minus 12x to find its y value. Negative 2 cubed is negative 8, minus x squared is 4, minus 12 times negative 2 is plus 24. Add those up and I get 12. So negative 2, 12 is a point on my graph. Now, the scale will be different on x and y in this case because my 1s are quite wide. Maybe I'll have a 10 about there, 2.5 blocks up, and I'll have a 20 there. X is negative 2, y is about 12. It's right around there. I could also plug in that x is negative 1 if I'm curious. Negative 1 cubed is 1, minus negative 1 squared is 1. Sorry, negative 1 cubed is negative 1. Negative 12 times negative 1 is positive 12. When I add those together, I get 10. So this is going to come back down near 10 and then hit that 0. Then again, we wonder what's happening here. You can plug in 1, 2, and 3 into your function and see what happens. I'm not going to show all the work for the sake of time. You know how to plug in numbers. When x is 1, y is negative 12. When x is 2, it's negative 20. When x is 3, it's negative 18. So again, I'll go for a scale so you can see the general features of this graph. So it seems as though it's going to look something like that. And for now, that's good enough. So again, when you want to graph a polynomial function and you're not allowed a calculator, know its degree and its leading coefficient sign so you can know its up down, its end behavior, and then know the y-intercept. Factor after that, get some good values in between, and do your best to get a general idea of the sketch. It does not have to be perfect beyond zeros and x-intercepts right now. Okay, let's look at another. For our second example, we'll look at f of x equals x to the fourth minus 5x squared plus 4. Well, here, my degree is 4, which is an even number, and it's a quartic function. And the leading coefficient, again, is positive. So this has end behavior that's up, up. This graph will start up and end up. We need to decide what's happening in between. I can also look at this function, and its constant term is 4, which means its y-intercept is 4. That's one accurate point I can plot. Now let's factor this to find zeros. So I have x to the fourth minus 5x squared plus 4 equals 0. Some people really don't like trying to factor with exponents other than 2, but it's necessary. And just keep in mind that math is consistent. I can split the middle on this and it'll help me. So I need two numbers whose product is 4 and sum is negative 5. Well, that's negative 4 and negative 1. So I'm going to split this middle, keeping in mind when you split that middle you keep the variable and its exponent. So this is negative 4x squared minus 1 more x squared. You bring down the front x to the fourth and the back term plus 4. When you do that and then cut it in half, your GCF on the left is x squared, and you're left with an x squared minus 4. On the right you can take out a negative 1 and you're left with your x squared minus 4. Now your factors are x squared minus 4 and x squared minus 1. Well, both of those factors are difference of two perfect squares, so I can factor more, and you always need to factor completely. So x squared minus 4 is x minus 2, x plus 2. X squared minus 1 is x minus 1, x plus 1. Setting all those factors equal to 0, I now have zeros or roots of 2, negative 2, 1, and negative 1. So I'm going to be able to get a pretty good picture of what this graph looks like. Again, I have a y-intercept of 4. I have zeros at 2, negative 2, 1, and negative 1. So I've got a lot going on between those little points. Remember, I have up, up end behavior. So this graph's going to start up and end up, and we need to figure out what's going on in between. Probably it's going to look a bit like a W. So what we can do is plug in, say, some point in between and figure it out. Or for now, just kind of guesstimate and say, well, it's ending down, but then it's got to go through that 0, so it can't have too big of a dip there. It's got to go through the y-intercept and do the same thing. I have a sense that this might be a somewhat symmetrical graph, just because of what I know about its factors. You don't need to know that right now, but again, you need to get a general sketch, being able to find zeros, y-intercepts, and end behavior from yesterday. In example 3, I have f of x equals negative x cubed plus x squared plus 3x minus 3. Well, this is a degree 3 function, which means it's cubic. Its leading coefficient is negative. So this is a reflection over the x-axis of our normal cubic function, which means instead of starting down and ending up, it's going to start up and end down. So this graph's going to look something like that at its ends. Again, we can look at the graph, see the constant term is negative 3, so that is my y-intercept. Now this has 4 terms, so immediately I'm going to split it in half and work on a greatest common factor. I never like having a negative leading coefficient, so I will factor out a negative. And my common factor on the left is x squared, so I'll take that all out. If you think about what root 3 must be equal to without a calculator, I know that the square root of 1 is 1, and I know that the square root of 4 is 2. So the square root of 3 is somewhere between 1 and 2. It's going to be 1 point something, and probably a little bit closer to 2. Maybe 7 or 6. I'm not sure without a calculator. But that, again, for the sake of these kinds of graphs, that's enough. So I can start my quick sketch. I'll start with my y-intercept of negative 3. I have a root of 1. I have a root of positive root 3, which I think is around 1.7. So there's 2 right around there. And negative root 3, so it's around negative 1.7, so right around there. Again, I'm curious about what's happening between my critical values. Again, I know that this starts up, so it's going to do something like this. And it ends down, so it's going to do something like this. Beyond that, I really don't know, and I need to get some sense of its features. So maybe I plug in x equals 1, just to see how far down that graph goes at that point. And I have negative x cubed plus x squared plus 3x minus 3. And I'm actually plugging in negative 1. That's a negative 1 over there. Now be careful with your exponents. I have a negative x cubed. Negative 1 cubed is also negative 1, so that becomes positive 1. Negative 1 all squared is 1. 3 times negative 1 is negative 3, and then subtract 3 more. So I have 1 plus 1, 2, minus 3 gives me a negative 4. So when x is negative 1, y is negative 4. So it's down here about. And so it probably turns somewhere near there, goes through that y-intercept, back up here, and probably must have a little peak in there somewhere. And again, that's good enough for now. You need to know your end behaviors, y-intercepts, and zeros. I have f of x equals x to the 4th minus x cubed minus 4x squared plus 4. We'll do the same thing. So let's try to factor this. We have 4 terms already, so we can split the middle. On the left side, I can take out a common x cubed, and I'm left with x minus 1. On the right side, I can take out a negative 4, and I'm left with x squared minus 1. This is interesting. This is nothing we've factored before, and it's a bit of a sneak preview or foreshadowing for what we're going to be doing later this week. One of the factors of x squared minus 1 is x minus 1. So it seems like there's probably a factor of x minus 1, or a 0 at 1. But I'm not too sure. So this is a case where really we're going to rely on a table of values to see what's happening with this graph and go from there. So here I'm going to make a table of values to plug into x to the 4th minus x cubed minus 4x squared plus 4. When x is negative 2, we get a y value of 12. When x is negative 1, we get 2. When x is 0, 4. That should not be a surprise because that's my y-intercept. When x is 1, I get 0. Here, there's a 0, which means x minus 1 was indeed a factor. We kind of thought so. Now we know for certain. And we'll talk about y again later. That's a bit of foreshadowing, like I said before. When x is 2, y is negative 4. And when x is 3, y is some big number. So we can draw a quick sketch. When x is negative 2, y is 12. That's up here somewhere, and I know it starts up, so I'm going to put my arrow there. When x is negative 1, y is 2. And then when x is 0, y is 4. So I don't have an x-intercept on the left side. Maybe I have an imaginary root over there. When x is 1, y is 0. So I must turn around here somehow. When x is 2, y is negative 4. And when x was 3, we got a really big number, and I know it needs to end up also because of the end behaviors. So it must do something like that. Again, good enough sketch showing me you know key features, degree, end behaviors, y-intercepts, and how to factor and plug into tables when possible. That's it. Have a great night.